we just discussed general questions, problem solving.
We've been doing 3D vectors in school.
Oh, you're studying a 3D vector. Oh, that's something new. Yes.
Yeah.
Do you,
And
do you want to show me your textbook from your side, or?
Yeah, I'll just open
Okay.
it.
One moment, I will let you go. Oh, you are studying the 3D vector now.
Mhm.
Right.
Oh.
Yes, vectors, product, scalar product. Yeah, we begin with scalar product.
I'm a bit confused on how to do these things, like determine a B vector.
Uh-huh. So you mean the product or the sum? They have 4 rows: sum, difference, product, right?
Mm-hmm.
They have 2 types of product. One is called a scalar product, another called the vector product. Are you talking about the determinant?
I don't know. It just says it
Which
says
one?
these
No,
things.
15? Are you talking about?
Yeah, 15A.
Okay. 15A. Okay, let's have a look. How can we participate? I can't annotate.
Yeah. I think if we just write down this and then, because I don't think you can annotate.
Okay, I have a look. So they have triangle A. Yeah, they have a triangle A. Yes, that is a 2 straight line in the 3D dimension. Yeah, I can write down here. Determine the names, right? Determine the names.
Yeah.
Can we copy the 2 vectors? Can we give me a few moments? I copy the 2 vector. Where is now?
This thing is very glitchy.
Here, number 15, right? So OA from origin is 2 1 2, okay, and OB is -1 -2 2. Got it? Okay. Let's go. Whiteboard. Yeah, 3D. So you have to. So basically, you have to learn how to draw the 3D diagram. When we study this 3D vector, I want to do some 3D diagrams. So there's 3D diagram. This X, Y. Oops, sorry. So basically, we have that is a convention. This X is Y is Z, right? Z is a vertical. So in this case, basically, you have to write this origin, right? This origin. So we basically have 2 points, A and B, right? A is X equal to Y equal to 1, Z equal to 2, somewhere here. You see, so this is can you see this is A, right? This is point A. Point B is -1, -2. So this will be other side. So 1, 2, and +2. So Y, Z will be somewhere here. The same amplitude, I think, very close to this. There will be the B, can you see? Roughly, it's roughly. So that is 2 points. And you have to know how to draw the 2 vectors. So this vector is one is OA, can you see? Yeah. And another is OB. So that is the 2 vector in question. So if I just write this vector given, so basically this is OA. I can either use the there are 2 types of notation. You can either use 2, 1, 2. This is a matrix notation, or you can use AI, IJK, right? is ij. They are equivalent. These two notation are equivalent. Actually, the matrix is faster.
Yeah.
OB. So what? Just I wrote the two notation: -1, -2, positive. So that is a 2 or negative. Sorry. -I, -2j, and positive k. That is the question. All right. So the question is to find what is the OA, right? AB, right? AB will be the names, you see. So in this diagram, you know that AB will be here. That will be A and B. That is names, all right? So you can work out this. Is actually the distance between 2 points, right? So how can we work out this distance? Any formula you have learned so far?
Is it Pythagoras?
Yeah. Can you write it down? You can use either dot product. Yeah, you can use a scalar product. Yeah.
Could you use Pythagoras for this, or?
Well, you see, if you know the two positions, so you can actually these two positions were actually what if in terms of the, can we say, I just need to know how much do you know, because if you ask me to solve this problem, I simply consider this vector form first, right? In terms of vector form, so in this diagram, I can see is I can write down here. So basically, the OA, so OA takes OB, right, or equal to BA. You agree?
Yeah.
So do you know use this formula, or do you have other formula? Or you can say the dot product.
I'm not sure because I don't know how to solve these yet, which is why.
Well, it's a distance, isn't it? It's just a two distance. So basically, if you want to work the distance, you can this is how to say this you can use you can find the angle first. Okay. If you can find the angle, then we can use cosine. We can use a cosine rule to solve this problem. Can we?
Yes.
Okay. So if you use a dot product, if you don't use this difference, you can just you just consider this a dot product. You see. So basically, the AB. Can we just use the dot product of these two? So you can make the argument starting from OA dot product OB, right? Or equal to the cosine theta, right? Equal to cosine. You have to find the cosine theta, or you have to the you have the OA. You have found OA without the arrow, which means the distance, right? Then you have plus the cosine theta. So in this way, you should be able to find the cosine theta. You see that?
Yeah.
Okay, that would be the cosine theta. We're equal to the dot product. See, that's two. Do you know how to find the dot? What is a? I just read the formula first. That would be OA dot product or scalar product divided by these two distance. Can you see? The OA and OB. Okay, this. So then, if you know the cosine, we should be able to find the third distance in this triangle. Can you imagine there are three triangles here?
Yeah.
Now, to find this, to find the cosine theta before we use the cosine rule, you have to tell me how to work out the dot product. Did you know how to use the dot product of two vectors?
I forgot. I did learn it. But...
in this case, you just use the component multiply components. So in this case, you just use the 2 multiply -1 plus, can you see?
Yeah.
1 multiply -2 and plus 2 multiply 2. So you just use components, multiply components. That is the formula, can you see? This is the first components, right?
Yeah.
And this is the second components. Okay. Can you write a formula for you? So if you have if you are looking for the, where should I put it? Yeah, put it here. Yes, here. So if you have A dot B, okay, that will, if you use a 3D, if you use a 3D form, and that would equal to A X BX plus AY BY. Do you know this formula now? AZ BZ. Okay.
Yeah.
So in the vector notation, so this notation, so this is actually, if you use a matrix form, that's just OAX, right? OXY and OAZ. Do you know? So therefore, what I pick up these 2 pair, if I use coloring, so this would be our first 3 number. 2 is here, can you see? Positive 1 is here, positive 1 here. Another 3 components, if I use yellow color. So that would be -1, can you see? The first one, -2, and the positive 1. That's it. Just use you don't need a calculator. In this way, you can find the product, a dot product. Can you?
Yeah.
You want to try?
Wouldn't it be 0 for this?
Could be 0. Really? I'm not
because
sure.
Because -2 minus 2 is -4.
Oh yes, it is 0. Oh, dot product 0. That's interesting. That's a special angle, isn't it? Okay, if that is 0, we don't have to go to, certainly the length is not equal to 0, all right?
Yeah.
Okay, if that is the case, and so therefore, we can argue that the cosine theta will equal to 0. Do you agree? So if the cosine theta equal to 0, what would be the theta?
45. Wait.
What is special
45
angle?
degrees?
45, are you sure?
I think.
Yeah, you have to combine your knowledge now. You have to put all this graphic stuff here. So if you have sine, cosine.
Oh, I meant 90. Sorry. 90.
Yeah, that's right. That's right. Yeah, that's right. Yeah. Sometimes you have to warm up. So that's cosine. Do you agree? So that would be for cosine, it would be 0. That would be half pi. Yeah. Perpendicular, isn't it? So these this actually in our case, these 2 sides are perpendicular. Okay, now that is one gradient we need to use. Another thing we need to use is apart from the angle, we have to, this is right angle triangle, isn't it? Oh, that's simple. It's right angle triangle.
Then we just use Pythagoras.
That's right. It's right angle triangle. If it's not, I just give in general, I just give some remark here. So in general, if theta is not equal to half pi, then you have to use the cosine rule, all right? Cosine rule. You know the cosine rule? Yeah, arbitrary angle triangle. Yes.
That's the.
So this cosine rule. Can we just draw this cosine rule? Yeah, this is you're in year 12. You have to dealing with combination of problem, right? So in this case, if this theta is not a right angle, so if this not the right angle, you have to use this. Can you see? You have to use this ABC, right? So you have used what do you know? Do you know the formula that is a corresponding? So this is so what is C? C squared equal to A squared plus B squared, take AB or take AB cosine theta. Double check, is that cosine rule? Check the cosine rule. This is cosine rule. You forgot?
Yeah.
Yeah. You have sine rule and cosine rule. Do you remember? This is a cosine rule. So that is general method.
It says it's 2AB cos A. Well,
You can write down
cos
here. What did you say? Can you write down here? Oh, this is A, so it's corresponding. Yeah, that is an angle C. Yes, that's correct. Yeah. So what, there are different
AB cos C.
Yeah.
2AB cos C, I think. Yeah, it's 2AB cos C.
Can you write down? Can you write cosine rule over here? Cosine rule. If that is a condition, C squared, yeah. You got a 2. Yeah, I forgot the 2. I got the 2 here. Yeah, all right. So that's right. Of course, in your case, this term vanish. Can you see that? This term vanish because cosine theta equal to 0. You agree?
Yeah.
So you are lucky. So that is a general method to solve this problem. First of all, you need to know how to work out the dot product of two vectors. Can you see? So this is the first piece of knowledge you have to get familiar with. Second, then you have to invoke the cosine rule. Of course, the special case is Pythagoras rule. Can you see? If you just get this part, is Pythagoras rule. Can you see that?
Yeah.
Okay. Next question.
Yeah.
You can copy if that is the case. Why don't you copy your question onto the whiteboard? We can solve together. Any other question you want to solve?
We just really started doing.
Oh, this is not starting. Actually, if you just starting, then you have to perhaps I give you some introduction, right? You how to denote basically in a 3D I remember before this students are required only study the 2D vector, right? It's 2D vector. Is there some similarity and also difference? However, if you're dealing with if you're dealing with 3D, you have to use your imagination. That's you have to use it. Sometimes you have to draw the 3D diagram. That's a little bit the challenging part for students. But in the 2D, we know that we can only use the two dimension. But in the 3D, we have used the 3D convention. When we use the 3D, we always obey the right-hand rule. In physics, do you remember the right-hand rule? So when you do x, y, this is x, y, z, we have to follow our right-hand rule. So this is x1, this is y1, this is z1. Now these are the three. That is a 3-unit vector. We have used it today. Can you see that? That is I. This is j. This is k. That's a 3-unit vector. In the 2D, we only use use 2. Perhaps we need to do this comparison, right? Yeah. That is special case. So this in the 2D diagram, we only need to use 2 directional vector. This is some basic perhaps we need to do. If you just start this chapter, that is something we need to do some review, okay, a comparison. So this is origin, you see? I just get familiar with notation. And this is y equal to 1. This is y equal to +1. Of course, this is y equal to -1. This x equal to -1. Can you see that? This is y equal to -1. what I'm talking about the right hand rule is that if you put the right hand, if you use the right hand forefinger to go from the x-axis to the y-axis, right? So from x-axis and rotate it into y-axis, right? And the sum will give you direction of z-axis. Can you see that?
Yeah.
Can you use right hand? For example, I give you some exercise to do. If I have, for example, if this is I get to some. This is just an example how to apply the right hand rule to determine the x, y, z direction. So in mathematics, it's just convention. But in physics, we have this direction will determine the direction of particular force. You remember when we started magnetic field. So that, for example, and if this is a y-axis, can you determine the y? Can you determine y? Can you determine x and y-axis in this diagram? So if this vertical represents y, what would be the y? What would be the x and y-axis? Sorry, what would be the what would be the x and z-axis? So you have to try to use the right hand, right? That would be the x. Oh, nearly. You can certainly assume this is you can assume this x-axis, but once you assume this is x-axis, this would be a negative z. The positive f should be here. Can you see? Just if you rotate is 90 degrees, and is a vertical one or the perpendicular, just like a thing. Can you imagine this is a circle? Can you see that?
Yeah.
When we use the right hand rule, we just follow the circle, isn't it? From x to y axis. But our sum, do you agree? If you if you use the right hand, the sum will always give you the direction of z. See that? In this case, you can imagine you can draw the circle in this x, this is called the xy plane. You see? So this is called the xy plane, plane surface. Can you see that? So you can imagine that the z is always perpendicular to this surface, right?
Yeah.
Now just drive my, so this is called I. Okay, that's when you're notation. This is called I. This is called J. Did the teacher tell you this is I? Can you see this direction of x-axis? This J is the direction of the y-axis, and this is the direction of K is direction of z-axis. So all of them is called the unit vector, unit directional vector, the directional vector. Because why is unit? Because or unity. Because the amplitude is 1. You see? So this is I, just Y here. So that is I, J, K. The amplitude of this one are always equal to 1. This amplitude, right?
Yeah.
For any vectors, okay, we discussed 2 vectors in the first example. For any vectors, we can always use combination of these 3, or in the 2D, we can use the 2 directional vector to work out this vector. For example, if this vector is called, say, called A, can you capital vector A here, right? So you can always find their projection, can you see, in these 2. So that would be the AX components. There will be the AY components, right? So if you in this case, if we just in this case the vector, any vectors or sometimes they just called OA. Can you see that?
Mhm.
Because that is this, if this position is called A, I don't want to make it too complicated. If this point is called A, I just use A, okay? I just discuss one thing, one issue at a time. For the vector A, we can rewrite this as X components multiply the I, that is the notation we just have used.
Mhm.
X, Y component multiply the J, okay?
Mhm.
Because that is based on our knowledge of the sum. So if you have two vector, I use different color. If you have two vector, so if you have this is vector, and this is another vector. You see? And do you remember what is the general way to work out the sum of two this vector?
Add the scalar like dot product.
No, the sum. I'm talking about this one. Can we call this is can we call this is
Pythagoras or like cosine rule?
no, can we call this side is our, yeah, we did, so this is this different color now. Can we call this is A, Y, J? Does that make sense? J is just unit, yeah? J, the length of J is unit. You multiply the scalar. So the components is a scalar, all right? You know the scalar. And the A is a vector. A is a vector. So the scalar, the vector can be written as a scalar multiplied vector. Okay, this is what this is 0. So this would be this side would be the AX multiply I. Do you understand? What is I? I is this unit vector is called I. Can you see? This unit vector is called J. So that is how we now. It would appear you have forgotten how to find the sum of two vectors. What you can do, we can
just add up the AX and the X values and then the Y values?
No, I'm talking about graph. How to use a graph to represent these two?
Oh.
Just like for two forces, how can we find resultant force? Can you try?
It should be head to tail, shouldn't it? You should flip this around.
That's not right. So that's why if you don't parallelogram, so that's right. So this is not right. This blue one actually represents the difference of two vectors. That's where you have to A, Y, J, take A, X, I. So that's why. Yeah, perhaps we can go to some more fundamental, all right? So in general, if you use a graph, we just pick the example. The two vector is not necessarily 90 degree. In our case, in our special case, is 90 degree, all right? But in general, you can consider any two vectors, the product, the sum of any vectors. So in this case, the angle may not equal to 90 degree, all right? So in this general case, in order to find the sum, you have to learn how, this is a more fundamental definition. You have to draw the parallelogram. You have to draw the parallelogram. And before we draw, can you see this parallelogram? And the sum of these two will be the diagonal. Do you remember this graphical method? Yeah. Of course, when you get familiar with that, you can say, well, we can put the purple one over here. Can you see that? That is what after you get familiar with this notation. So therefore, we turn to our question. The correct representation of this one, if you're looking for the sum of two components, it will be something like this. Can you get to that? So we have to draw this rectangle. Because it's 90 degrees, so we can draw a rectangle. after that, we can work out the sum of two vectors. You see that?
Mm-hmm.
So this will be our A vector. You agree? Well, I'm using the same graph here. In other words, this equation can be graphically explained by this graph. Can you see that?
Yeah.
Two vector whose sum will give to the vector. All right. So that is how to denote the vector. So that is how to denote a vector by its components. And unit vector. Unit vector is belong to X and Y axis. So that in summary, you have vector in the 2D, then we can write it into this form. We can write it AXI plus AYJ, okay? Mm-hmm. Alternatively, if you have studied some matrix notation, you can simply write that as A components, X and AY. Then in this case, you don't have to write the I and J.
Yeah.
So that's different notation. Now, expand this idea to the 2D. So this is 2D vector. So if you go to 3D, that is how we just encountered at the beginning of this talk, right? So we've got X components multiply I. That is this notation. You have to get very familiar with this notation. This J. In addition, we have a third component called Z as K. Again, if you use a matrix, that can be written as AX component and Y component and a Z component. You can see that. So in other words, if you have vector in a 3D, you would expect that in general, they have 3 components. Can you see? So this 3D must have the 3 components. If I just use as graphical. So if I just look down, right? If you just look down, then you will see the X component and the Y component, all right?
Yeah.
But if also look toward the direction, or make this longer. Also, you should be able to see the zeta direction. Can you see? That is zeta direction. So, in general, so if this R is also called the position vector. I give you another summary. So another important thing is the position vector. So if anything, if this position is called P here, of course P can be written by 3 coordinate, right? X, Y, Z. So the important vector is called the position vector. Position vector. It always from origin. Position vector also from origin, right? In this case, we just use R. Or if you wish, you can just use this notation like the textbook. Can you see? You can use OP. Can you see that? And for the position vector, we can always written this as xi plus yj and plus zk. Do you understand that?
Yeah.
Or you can use, if you use matrix, it's much simpler. That is x, y, z. You see that?
Yeah.
Now you have started calculus. So what is velocity vector? The velocity, okay, C. Velocity. Can you help me to write the velocity vector? Do you want to try?
Isn't it just the 2D vector?
3D. I'm starting 3D now. These are all 3D. You can start from 2D, but we are starting the both 2D and 3D. This is a kind of the border. Oh,
So there's a velocity vector.
by the way, this diagram can also apply either 2D or 3D, all right? Or 3D. That you can also apply this graph. Yes. Okay, can you help me to work out the vector of the velocity in 3D?
Does it not start at the origin?
The star, yes, you can use star. Yeah. Do you know the star notion? Can you write down? What do you mean star? Can you write?
Oh, I mean, like, it doesn't origin, it doesn't start at the origin. It's just in like floating in
yes.
space.
Yes, right. It's not from origin. So only this is only true for the position vector. When you use a straight, the velocity is, in general is not from starting. The velocity is the velocity of the particle. Can you see? You can think this is the velocity of the particle. Can you see? It could be any direction. Do you agree?
Yeah.
So it could be that direction. Yes. That's the velocities have nothing to. Yeah. The velocity is not. It's starting from the p, not from origin. Yes, you are right. So this is a velocity vector. Now, what is the relation between the vector? What is the relation between the velocity vector and the position vector? No. You don't have to write this one. Probably I don't have to write this one. You will feel confused. Because you use OP only for the no, not OV. Sorry. I think I should not discuss too much here. I just write R here, all right? Just R vector. Otherwise, you get confused. And we just discuss the position vector. Of course, the position vector starting from origin. Okay. Before that, what is the relation between the V and the R in physics? Assuming X are the function of time, and also Y is a function of time. So what is the relation between the position and the velocity? By definition, what is the velocity?
The speed at which it's traveling?
No, after you have started calculus, we should be able to use calculus to describe the definition of the velocity. Little bit of physics today.
Yeah,
it's very useful. I can tell you what, Victor is very useful for study physics. Okay, I write the question for you now for the first time. We have studied calculus, right? So that is how we use calculus to define the velocity for the velocity delta t and delta t approach to 0. Then by definition, it's just dr dt. Can you see? You do know why did Newton invented the calculus? Because you want to, yes, because you want to write the velocity in this way. Nobody had done that. So therefore, Newton is the first person who can describe the motion very accurately, right? Okay, this is a little bit of calculus. So when you do the differentiation, then what you do is you just do this x. Do you use this notation? Have you seen this notation before? The dot here.
No.
Oh, this dot here. So this x dot were just equal to dx dt. And the y dot will just equal to dy dt.
Oh, so it's just the derivative of x.
Derivative, yes. In other words, these are represent velocity along the x direction. If you use the 3 components, that would be velocity in the y components. You see, j, and that would be the velocity in the z components. This is k. Sorry, this is k. It's too small?
No, I see it.
All right, this is just introduction to how to denote the 3D vectors. And you can imagine this diagram is very useful. You can imagine that there is a, you see, there's object, can you see? You can imagine there's object flying, can you see? You understand? So you can imagine the object is flying. When the object arrives the P, and the position will be the, at this particular will be R, will be the position, can you see?
Yeah.
And also the velocity will have to be drawn very accurate. The velocity must be along the tangential direction, right?
Yeah.
So you can see that one of the important application after you study 3D vector, then is to describe the motion of particle in three-dimensional space.
Yeah.
All right. Why don't we return to your textbook to see the requirement? What did you know? Otherwise, can we just?
Do you want me to show you the syllabus?
Yeah, that's right. Because before you go further, because when you study 3D, when you study vector, you have eventually studied the plane, right? You will study how the relation. Because we haven't studied, we know how to draw the straight line in a 2D. Before you go, I just give you introduction. So basically, in this chapter, you will study in the 2D. We can only study a straight line, right? We can only study the straight line like this, right? A straight line like this. But in a 3D diagram, in a 3D space, we can study this issue became plane, you see. So you can imagine that the special case in our case, you can imagine there is a plane which is cut off. So this is a plane which will cut off two axes. Can you see that? So you can imagine this is a part of plane. Let's draw that. So that is one direction you want to go. Can you see this triangle is in the same plane of this rectangle?
Yeah.
So you can imagine that we studied the how do we describe this direction? Then we have use vector. This is called the directional vector of the plane. That is eventually going to learn. Can you see? I can introduce the vector, and this vector must be perpendicular to this plane. Can you imagine this triangle plane in the 3D? And this n is called the direction of this plane.
Yeah.
So in the 2D, we can also introduce a normal direction. Can we? We can introduce a normal direction to the straight line in this normal direction, right? But the normal direction, this direction, if you still call it n, it's just two-dimensional, right?
Yeah.
We got for the n can be written as say ai plus bj, right? But in this case, in the 3D, and n must be written as 3 components. aj, I, can you see? bj plus ck. Can you see?
Yeah.
All right, let's go to your textbook. Let's stop this.
I'll show you the syllabus first.
One moment. I just save this in case I forgot. Okay, I save this. Okay, you can go to your syllabus. You can use your textbook. We can see.
Says introduce the unit vector k and the altitude.
Altitude, yes, we're talking altitude. Sorry, magnitude, right? Magnitude.
Yeah.
I can't see your textbook. Did you share?
Oh, this is the syllabus.
Where did you display? On your screen? You can share your screen? You can share
I
your
am sharing it, I think.
I couldn't see it. Can't see it. Multiple participation can share simultaneously.
Oh wait, I'm not sharing my screen. Give me a second.
You share your screen, you can see. We need to see. That's right. I can see your screen now. Victor and the matrix. Oh, you're going to start the matrices at the same time. You see, we have this. That's why when we start the matrix, we can use the matrix form of vector. Let's go on. Subtopic will be. It is a syllable, right?
Yeah.
Determine the corresponding Cartesian coordinates, two-dimensional case is equation of straight line. Yeah, determine vector parametric Cartesian. Yeah, it's better to look at your textbook. This writing is very is a too formal, and just okay. You just go to the first chapter. You go to the chapter. We just scan this beginning of chapter now.
Yeah, this is the next chapter we're working on.
Yeah, that's right. You're going to say today we use the formula for the dot product, right? Or that is called the dot product is also called the scalar product. The dot product enable you to work out the angle between the two vectors, because the dot product including the cosine theta. That is the key. Can you see this formula here? Can you see? The dot product were equal to this is special case. That's a special case. Oh, we have encountered this special case today. Right? That's problem 15. So in the first place, you need to learn how to work out the angle between the two vectors given. All right. So that we have demonstrated how to do that. In order to do that, you need to find the dot product first and divided by his magnitude. That will give you the cosine theta.
Yeah.
Now this is how to find the dot product. Okay, yes. In this textbook, they both use this components form. It's called components form of vector. It's called the matrix form of vector. Okay.
Yeah.
And so these represent the same thing, that you just use the two components multiply. That is the definition how to work out the dot product. You can see. Yeah. Okay, we can scroll down to see other things. Second, you need to calculate the angle. Yes. Can you see? Oh, we cover a lot of the contents today. So that is formula. That is formula. Can you see? That is formula for calculate cosine theta. Or if you want to what are theta, you just found is inverse function. Can you see?
Yeah.
Yes, we use these two formulas. Yes. Okay, that's how they teach you step by step. That's how in this particular example they found this angle which is not 90 degrees. Can you see that? It's not 90 degrees. And then we're talking about projection. Yes, you have to know what is projection. You see, we jump today. Actually, in order to work out the components, what is components? The component is the length of the projection vector. The projection vector, can you see? The projection, if we go slow next time, take step by step. Projection is such, you have imagined there's a straight, there's a light source here at the top, like sun, right? The shadow of this vector will be called their components. Okay.
Yeah.
But when we discuss projection, we still use vector. So the projection in general is a vector. Can you see that?
Yeah.
So that's called the vector projector. And the vector projector, if we just consider this amplitude of vector project, that will be the components of the vector A along a particular axis. We can scroll down. Yeah, I know what you're trying to do. Can we just scroll down? Yes. We have covered a lot of content today. Yes.
Yeah, and then we just have the questions to do.
Yeah, that's right. You have to. Yes, you have to. How did you jump to 15? Question 15.
Oh, because I did the other questions before, but I didn't know
without
how to
without
do
teaching, without learning, you know how to do it, right?
Oh, they told us to do like basic. They told us the basics of 3D vectors yesterday, but I didn't know how to do question 15, so I asked.
Yeah, right. Well, yeah, this is just the beginning of to study the 3D vector. Can you scroll down? Can you scroll down? And yeah, this is let's go on. Yeah, you can go to next chapter, next section. Yeah, this exercise. Can we go down? This this linearity. Dependent on independent vector. Okay, that's gives some idea about what is a linearly independent, dependent or independent vector. Yeah. So then you are talking about the this is background. The background, the content is picked up from called linear algebra. So algebra can be divided into different detailed algebra. So this is called the linear algebra. So the two vector can be linear dependent or independent, depending on the slope. Now we have the three slope. Can you see? We have three. We have not the three slope. Rather, we have the three projections. So we can use this projection to make this phasor definition. Or we can study the property between the two vectors. Can we go on? Yeah, can scroll down. Yeah. So that is okay. That is notation for. Can you look at this triangle? This is notation for the difference. Can you see? That's notation for the difference. Can you see? So I have to be careful. I wouldn't start from this triangle. I would like student to start from the parallelogram, right? Because if you use a parallelogram, you know how to work out the sum in the first place. Okay. Come on. Yes. Yes. Dependent. Yeah, that's by definition. That's just dependent and independent. So you have to. They have some criterion for the depend whether the two straight line is a what two vector are linear dependent or not. Can we just go down? We just scan this chapter. Yeah, chapter 2. Go on. Yeah, that's a diagram I just drew. Can you see? Can you check if that satisfies the right hand rule? Where is the x-axis?
The x-axis, yeah, it follows right hand rule.
Yeah, that must be obey the fact rule. Vector proof, geometry, yes, that is application. Yeah. So sometimes we can solve the geometry problem by using vector, because that is this is new vector. Oh, can you see the parallelogram? So this should you should get familiar with the parallelogram first. Can you see? So this diagonal is a sum. Can you see? This diagonal is sum. Although sometimes we put the second vector in this position, right? And this is shorter that the shorter diagonal will represent the difference between the two vectors. Can you see?
Yeah.
Today you pick up the difference instead of sum. Okay. Doesn't matter. We'll get used to that. Yes, scroll down. Can you scroll down? We just go down. Yes, that's right. Yeah, you can do a lot of things by using a parallelogram. Yeah. Vector proof, geometry, yes, theory. Okay, you can apply for the circle, triangle. Yes, oh, that is 3D. Oh, that's interesting. Actually, you can use a 3D vector to work out the volume of this. Can we look at this name? It's very long name. This what is name for this? The parallelogram. You know this name? Can you scroll back? Scroll backward. Yeah.
Oh.
Oops.
Backward.
Just that one. Just look at the name. Yeah. Parallelepiped. Parallelepiped. That's right. It's a long name. It's just 3D. It started. It's just like in a cubic was would be how to say elongated or actually smeared. you have the deformed. Okay, right hand row. Can you see? We started right hand row today. Right hand row, yes. Right hand. Yeah. Yes. That's okay. Yes. Yeah, no problem. We can. Can we just go down? Yes. Can we see that circle I draw? Can you see circle?
Yeah.
Yeah.
We covered
Yeah.
a lot today in that little.
This data product. Yeah. You were knowing graduate. This now they are dealing with the cross product now. Can you see? Have you heard of cross product? Yes. Cross product. When we started the have you started? There is a Lorentz force. Do you remember? Do you remember Lorentz force?
What force?
Magnetic force. Not yet.
Not yet.
Okay. This year we're going to start in physics. We're going to study the magnetism, electromagnetism area. Yeah, that's right. That's right. Okay. Yeah. So this chapter is a bit of geometry and a bit of the linear algebra. So you have to get familiar with this 3D diagram. And all the pips, yes. Yes, that is diagram I draw you. Can you see?
Yeah.
In the plane, in the 3D, you have to get familiar how to determine the direction of this plane. Can you see?
Yeah.
So that is the vertical one. Can you see? This is in the plane. Can you see? It's in the plane, and this is perpendicular to the plane, or the normal direction of the plane. And because they are 90 degrees, so therefore you can argue that there are some simple relation in their data product, in the scalar product. All right, I think that's I know what I'm going to do. Yes.
Yeah.
We can continue next time. All right, shall we stop here now today?
Yeah.
I will see you Friday, right?
Yeah, I'll see you on Friday. Thank you.
Physics, same time. Okay.
Oh, is it at 5:30 or 4?
Yeah, we can 5. You can start at 4. Did you start at 4? Yes. Yeah. 4. Yeah. Yeah. That's right. Thank you. See you at 4.
Okay. Thank you. Bye.